Hi and a very good day I bid to all of you. My name is Siti Sofia binti Abdurrahman. My matrix number is CD240321. Today I'm going to present about abstract. So firstly, in this report, we will analyze several real incidents. For example, Alaskan incidents and others. So basically, we will talk about engine failure, pressurization, landing gear and electrical failure. So the key findings in this report is about a system closely connected, and also failures may impact flight safety. From this report, we can learn also about the importance of redundancy, monitoring and entrain crew to avoid all the incidents. Next, we will also learn about goals that we need to reduce failures in order to improve the safety of the aircraft.
Modern aircraft commercial are equipped with a highly reliable and redundant system designed to ensure safe operation. Despite this, the complexity of the system means that failure can still occur and lead to the critical emergency. This project focuses on 4 major aircraft systems such as engine, pressurization, landing gear and electric system whose failure, if not managed properly, which could endanger both the aircraft structural integrity and the safety of passenger and crew. The primary aim of this report is to explore how the system responds during emergency or malfunction scenarios. By analyzing real-world incidents, this project examines the causes of failure, the method employed to manage this failure in flight, and the lesson learned. To structure this investigation, the report applies the DMAIC, which is define, measure, analysis, improve and control methodology, which is ensure a systematic and improvement focuses analysis of the system performance during failure event.
Next, I will explain about the engine failure. In flight, engine failures are critical emergency that affect flight safety and operation. There are 2 major incidents that happen, which is United Airlines Flight 328 in 2021 and Southwest Airlines Flight 1380 in 2018. There is exposes weakness in inspection and response procedure. United Airlines Flight 328 experienced an engine failure after the takeoff from Denver due to a fractured fan blade causing debris and fire, while other one, which is Southwest Flight 1380, suffered a fan blade fracture that led to window damage, cabin decompression and 1 fatality. Investigators collected engine performance data, maintenance record and metallurgical reports. They also reviewed debris pattern and how the crew handled the emergency. Both failures were caused by undetected fatigue cracks in fan blades. All the inspections techniques were not sensitive enough. UA328 also faced a nickel fire due to design flaws, while WN1380's issue was missed during a prior overhaul. How we can improvise this? New inspection methods like ultrasonic and eddy current testing were adopted. Maintenance schedules become condition-based. Fan blades were redesigned, nickel strengthened, and predictive tools like oil analysis introduced. Crew training was updated for better emergency handling. Regulators such as the FAA now audit maintenance practices regularly. Airlines updated the manuals and integrated real-time monitoring system. Continuous collaboration across the industry ensure that ongoing improvement in engine safety and reliability.
Okay, so next I will explain about pressurization problem. for define. Aircraft require pressurization at high altitudes to ensure passenger safety. Cabin pressure is regulated to simulate 4,000 to 8,000 feet to prevent hypoxia and discomfort for the passenger. A major failure occurs when a door plug detached mid-flight, causing rapid decompression, which this incident happened in Alaskan flight. This study aims to identify and fix design, manufacturing, and inspection flaws. So, for measure pressurization failures make up 2 to 4% of aircraft system issues. Common causes include valve faults, sensor errors, and fuselage leaks. Delta Flight 1213 had a pressurization alert and returned safely, while Alaskan Flight 1282 experienced a door plug blowout, leading to mass aircraft inspections. So next, for analyze, the Flight Delta 1213's issues stem from a faulty sensor and one valve actuator. Alaska 1282's failures was due to door design flaws and poor maintenance. Both incidents stress the importance of strong inspection, quality control, and timely maintenance to avoid serious safety risks. So for improve to avoid this problem, to reduce pressurization failures, improvements include standardizing door plug installation with clear guidelines and visuals, dual technicians sign off, and smart fasteners or torque sensor can ensure proper bolt tightening, adding tamper evidence seals and enhancing technician training on safety critical component will also improve system reliability. Next, what we can control is to sustain improvements and routine audits and inspection of pressurization, which is the critical parts like door plugs or are essential. A digital tracking system should log maintenance action and technicians sign-offs. QR code tagging can improve traceability, while automated alarms can alert teams to miss or overdue maintenance tasks. I think that's all from me. Thank you.
So next is the landing gear system. The landing gear system is responsible for supporting the aircraft during takeoff, landing, and taxiing. It consists of hydraulic actuator, structural assembly such as the strut and axle, electrical signal system, and mechanical locking mechanism. Failure in any of these components can result in landing malfunction, such as failure to deploy or retract, asymmetric extension, or collapse under load. Landing gear failure are particularly critical because they tend to occur during high-risk flight phases, during takeoff and landing, where quick pilot response is essential. This failure can lead to several consequences, including runway exclusion, structural aircraft damage, fire due to fuel line rupture, and even fatalities. From an operational perspective, the result in emergency landing, airport closure, flight delay, and cost repair. According to the malfunction of the landing gear system, so the first one we have the American Airlines Flight 383. The incident was initiated by a catastrophic uncontained engine failure during the takeoff roll. The explosion from the engine released debris that struck and critically damaged the main left landing gear and nearby fuel system. The damage caused the gear to collapse under the braking forces, leading to a fire and high-speed rejected takeoff, which is RTO. Investigation revealed that the engine's turbine disfailed due to the metal fatigue, which had not been detected during regular inspection. The incident exposes not only engine design vulnerabilities but also the lack of shielding between the engine and critical landing gear structure. The second one, we have the Qantas Flight 72. The aircraft nose landing gear failed to deploy properly during the approach phases. The onboard system indicated an incomplete gear extension. After performing a go-around, the pilots initiated the manual gear extension process, which proved successful. Post-flight inspection determined that the nose gear hydraulic actuator had suffered internal leakage, likely due to wear and undetected corrosion. While the crew handled the emergency effectively, the case highlighted deficiency in predictive maintenance system and limitation in detecting hydraulic degradation before failure. To reduce the risk of landing gear system failure, several improvements are necessary. First, introducing enhanced material and coating is crucial. This involves using corrosion-resistant alloy and anti-fatigue coating for gear axle and hydraulic actuator, particularly in high-cycle commercial fleets or aircraft flying in coastal and humid conditions. Next, real-time gear health monitoring should be implemented by equipping landing gear with smart sensor. This sensor will measure stress, hydraulic pressure, and locking status in real time, allowing for predictive maintenance and enabling crews to receive early warnings of potential issue. Additionally, structural shielding improvements are necessary to prevent secondary damage from engine nacelle and landing gear assemblies. Another key improvement is updating crew emergency procedure training, ensuring the pilots and ground engineers are prepared for landing gear development anomalies, manual extension drill, and asymmetric gear response. Lastly, maintenance protocol enhancement can be implemented by introducing automatic inspection alert by hydraulic and actuator component based on gear usage cycle rather than relying solely on calendar-based interval.
Hello doctor, today I'm going to present electrical system. Our view is electrical failure is in aircraft can disrupt key functions such as engine, control, navigation, communication and flight instrumentation. These failures are particularly dangerous due to their cascading effects. The notable incidents are British Airways Flight 38 2008 electrical failure led to a dual engine flame out during the final approach. Then another one is Delta Airlines Flight 9570 in 2022. Partial electrical failure caused temporary loss of instruments linked to wiring faults. The root causes lack of redundancy in electrical systems, aging wiring and degraded connectors causing intermittent faults, design vulnerabilities in critical power supply components. The ways to improve to avoid this kind of incidents, enhance redundancy, multiple power sources like APUs, auxiliary power units and backup batteries with automatic switch over. And second one is wiring and connector quality. Use corrosion resistant materials and vibration resistant connectors. And real time monitoring. Install sensors for early detection of electrical degradation. And crew training. Update simulator scenarios for managing electrical failures. And then finally, in a nutshell, electrical system failures highlight the importance of improving redundancy, wiring integrity, and proactive maintenance. Enhancing these systems can reduce the risk of in-flight failures and improve overall safety.
For the conclusion, this project applied the DMAIC methodology to systematically investigate for critical aircraft system failures, which is engine failures, pressurization problems, landing gear malfunctions, and also electrical system failures. By clearly defining the scope and significance of each system failures modes, measuring their impact through analysis of real-world incidents and identify root causes, the study provides comprehensive insights into the vulnerabilities that threaten the flight safety and operational reliability. The analysis revealed common themes across the system, including the design limitation, maintenance challenges, environmental factors, and also the need for improvements, redundancy, and fault detections. In each case, failures events underscore how single points of failures can cascade, leading to complex emergencies requiring rapid and effective crew response. To address this issue, the project proposed targeted improvements such as enhanced inspection techniques, advanced monitoring technologies, improved materials and design modification, and updated crew training protocols. These measures aim to prevent failures, reduce risk, and also improve the emergency handling capabilities. Sustaining these improvements require robust control measures, including regular audits, predictive maintenance program, and regulatory oversights, and continuous crew preparedness. Ultimately, this project emphasized the critical importance of ongoing risk assessment, system resilience, and proactive safety management to safeguard passengers, crew, and aircraft operations in an increasingly complex aviation environment.